So we learned a bit about complex ions in an earlier chapter. Right here we have a complex ion. We have a central metal ion surrounded by ligands. So these ligands are Lewis bases. They form a bond with the metal. Well, you can't just have ions in a substance. You can't just have positive ions. There's got to be some counter ions to balance the charge. So the complex ion will have counter ions, and so together these make up a coordination compound. If it's an aqueous solution, of course the counter ions are going to be off swimming by themselves. But if you have the pure solid, you're going to have the chloride ions right in here with the complex ion. So coordination compound, neutral compound consisting of complex ion and one or more counter ions. So the metal ion in that coordination compound has two types of interactions. The first type is what the oxidation state is on the central metal ion. And that's referred to as primary valence. The secondary valence or coordination number is how many molecules or ions are directly bonded to that metal ion. So these are the ligands. So as an example, we're going to look at this compound, CONH3 6Cl3. We're still generally looking at ionic compounds being two ions, a positive ion and a negative ion. But now some of those ions are getting a bit more complicated. So here's our positive ion. So we have a cobalt ion, and it has 6 ammonia molecules bonded to it. And then we have these 3 chloride ions. So what's the primary valence here? What's the charge on that cobalt ion? Well, let's see. How do we think about that? Okay, I'll have to piece these back together. I forgot where I was, but that's okay. Okay, so secondary valence, this is asking how many things are directly bonded to that central metal ion. So here's our complex ion. How many ligands does it have? It's not a trick question. How many NH3s are in that formula? 6, thank you. They're alive. Okay? We can form very, very similar compounds that yet are different. We could also have CONH3 5Cl2. So now one of these NH3 groups has been replaced by a chloride ion. And then we only need 2 chloride ions to counter. Or we could replace 2 of those NH3s with chlorides. And now we only need 1 as the counter. So those ligands and counter ions, it's possible for them to switch places. That makes it a different compound. Could NH3 be a counter ion? Is it an ion? Is NH3 an ion? No. NH4 is an ion, but NH3 is not. So here, let's just look at this last one here. So the cobalt is going to have 4 NH3s. And also 2 chlorides. And that's an ion. So this cobalt still has its +3 charge. So then when we look at this whole thing, we've got +3, -1, -1. So this is a -1. +1. That's what I meant to do. And so we only need 1 chloride ion now as the counter ion. So complex ions has kind of got multiple meanings. These are complex. They're kind of complicated. So a complex ion is a Lewis acid-base adduct. We talked about Lewis bases and acids back in, I think, chapter 17. So a Lewis acid, well, let's talk about Lewis bases. So Lewis bases are electron pair donors. So here we have our transition metal ion, a silver ion, and here we have two ammonia molecules. These are good Lewis bases because they have a lone pair of electrons they can donate. Silver is a good Lewis acid because it's good at accepting electrons. It has no lone pairs on it. So the way this works is this is going to make a coordinate covalent bond where the Lewis base is going to donate both electrons for the bond. So these two electrons in this coordinate covalent bond both came from the ammonia. So it's being very generous in sharing with silver. And here's the other ammonia also being very generous in sharing with silver. So it's different than a regular covalent bond where each atom contributes one electron. They both share. So the ligands are good Lewis bases. They're going to have at least one lone pair. Any questions? So these are some common ligands. And if we look at their Lewis diagrams, what we see is that they all have some lone pairs. Water has two lone pairs, so it can form a coordinate covalent bond with a lone pair. Ammonia, the chloride ion, has four lone pairs, so it can form a coordinate covalent bond using one of those lone pairs. Carbon monoxide, the cyanide ion, the thiocyanate ion, the oxalate ion. We've encountered thiocyanate and oxalate in our experiments in lab. We've used oxalic acid and like potassium thiocyanate. And then there's two that are very common but more complicated. This one's called ethylene diamine. And the diamine is because it has two amine groups here. These are like ammonia, right? Where instead of a hydrogen over here, it's attached to this ethylene molecule. And there's two of them. So ethylene diamine. That one has an abbreviation for its name, EN. Oxalate is abbreviated OX. And then this guy's even more complicated, ethylene diamine tetraacetate, or EDTA. If you look at ingredients on consumer products and on some foods, you may see EDTA in the ingredients. And that's what this is. So here on the EDTA, we see that some of these lone pairs are in red. There's lone pairs all over the place. But the ones in red are the ones that can form coordinate covalent bonds with the metal. And so this one actually can form 6 coordinate covalent bonds. Many of the ligands can only form one bond, donating only one pair of electrons, and those are called monodentate. I don't know why dentate. Reminds me of biting, but monodentate donate one pair of electrons. Bidentate donate 2 pairs of electrons. So oxalate and ethylene diamine are both bidentate. We have ethylene diamine. It's got a lone pair over here and a lone pair over here. And so it can use both of these with the same metal ion and form 2 bonds. Then we also have polydentate, which is more than 2. So ethylene diamine tetraacetate ion is an example of that. I'll go a picture of that one, yeah. So this is a hexadentate ligand because we've got 6 different lone groups or lone pairs that can form a coordinate covalent bond. So here we have ball and stick models of cobalt with the bidentate ligand, ethylene diamine. Let's see if we can kind of highlight this. So this is one of those. And let's see, this one is another. So it kind of bends around and both ends attach. And then we've got this guy. So there's 3 ethylene diamines, and they're each attaching twice. And then this one, we have 1 cobalt ion and 1 EDTA ion. And so it's making 6 bonds with the same ion. Let's see, what would be a good way to show this? Yeah, let's do a different color. So there's one here, and here, and here, and here, and here, and then the other one is going down to that oxygen down there. So it wraps and folds around and actually shares 6 pairs of electrons. So when you have a complex ion with a bidentate or polydentate ligand, these are called chelates. It's a special group of complex ions. And so EDTA is referred to as a chelating agent. Any questions? The coordination number, that secondary valence, we see coordination numbers varying from 2 up to 12. 4 and 6 are the most common. 2 will occur with positive 1 ions. It's not as common. In the first row of transition metals, we're only going to see up to 6. It's possible to have odd numbers, but those are rare, so we're not going to talk about them. The geometry that they form depends on the coordination number, but also on the number of d electrons in the metal ion. And so this relates back to VSEPR theory. So the coordination number is like the number of groups attached to the central atom. Coordination number of 2, you're going to get a linear shape. They're going to be attached on opposite sides. 4, what we're most familiar with is tetrahedral. So that's when we have 4 electron groups around a central atom. Square planar is also possible with 4, but in VSEPR theory, then we needed to have 2 lone pairs here. So whether 4 ligands makes square planar or tetrahedral is going to depend on the d electrons. And then octahedral is what we get with 6 electron groups or 6 ligands. It's going to form an octahedral shape. And then we're going to learn how to name these. And the great news here is that this material is not on a regular midterm exam, right? So you don't actually have to hold all of this in your brain for an exam. You will be naming things on your take-home exam, but you can look at the rules. So let's just talk about this. So as with all nomenclature, we have a series of rules. The general idea in nomenclature is that each individual substance will have one best name. Sometimes there are other names, like water has 2 names, right? We call it water, but it could also be called dihydrogen monoxide. But we have one best name. So we follow those rules to get this best name. So first we have to name the ligands. So the neutral ligands are named as molecules, but there are 3 exceptions. So this is water, ammonia, and carbon monoxide. but they don't have those names as ligands. H2O is called aqua, NH3 is called amine, and CO is called carbonyl. And then we're going to name any anionic ligands, and we're going to take the name of the ion and change the ending to O. So chloride becomes chloro. Sulfate becomes sulfato. And sulfite is sulfito. Then we're going to list those ligands in alphabetical order by their names. So we put them in alphabetical order because we want to have one best name. We want everybody to come up with the same name. So there's no options in which one you put first. Put them in alphabetical order. So the example here, if you had amine and chloro and nitrito, amine goes first because A comes before C and C comes before N in the alphabet. Then we're going to use numerical prefixes to indicate how many ligands there are if there's more than one. These are the same numerical ligands that we used in naming molecular compounds. Di, tri, tetra, etc. So trichloro means you've got 3 chloride ligands. Tetraamine means 4 ammonia ligands. A little wrinkle here. What if the name of the ligand already has numerical prefixes in it? Like ethylene diamine. It has di in it. So we don't want to possibly mix up the prefix telling how many with any prefixes that are part of the name of the ligand. So we put that ligand's name in parentheses, and we use slightly different prefixes. Instead of tri, we're going to use tris. Instead of bi, it would be bis, and instead of tetra, it would be tetrakis. Those prefixes are not considered in the alphabetical ordering. So ethylene diamine would come before nitrito and not after it because you wouldn't consider the tris. So you nail down all those ligands first, and then you name the metal. We can have complex ions that are cations. We can also have complex ions that are anions. So if you have a cation, you're just going to use the name of the metal ion, well, the name of the metal followed by its oxidation state. So this is just like naming metal ions in nomenclature, right? So cobalt 3, platinum 2, copper 1. If we have a complex ion that's in an anion, the name of this complex ion needs to be different from a positive version, right? So we're going to change the ending of the metal's name. And we're going to drop part of the ending and change it to 8. So cobalt, there's nothing on the end to drop, so it's cobaltate. Platinum is platinate. Copper is not copperate. Here they go back to the Latin names. Copper is cuprum, and so this is cuprate. Aren't you glad you don't have to remember all this? So then what you do is you write the entire name of the complex ion. You list the ligands first in alphabetical order by their names, followed by the metal. So this guy, PTNH32Cl4 2-. So we have diamine, because we have 2 ammonia groups, and we have tetrachloro, and then this is a negative ion, so platinum becomes platinate, and then we have to figure out the charge on the platinum ion. So we've got negative, wrong pen, we have negative 4 from the chlorides, and overall this needs to have a negative 2 charge, so the platinum must be plus 2. So that's platinate 2. Diamine tetrachloroplatinate 2. Get some really long names here. This is a cation. There are 6 ammonias, so hexaamine. Those are neutral, and so it's easier to see that the charge on the cobalt is 3. Hexaamine cobalt 3. These are some tables that might be helpful to refer to as you're naming these things. You've got some homework problems to do in addition to that take-home exam. If we look over here, these are the common metals when found in anionic complex ions. The positive ones are easy, there's just the element name. But the anions are a little different. So, chromium, chromate, cobalt, cobaltate. But then a bunch of these are going to use their Latin names. So copper is cuprate, gold is orate, because the Latin name for gold is aurum. That's where a symbol AU comes from. So a bunch of these are going to have these funny names, like silver is argentate and tin is stannate. So that was naming complex ions. To name a coordination compound, you name the complex ion and the counter ions, and you put them together. Positive ions first, negative ions last. What about writing the formula for a complex ion? Well, you do this in kind of reverse order. Instead of starting with the ligands, you're going to start with the metal. So you identify the metal and its charge from the name. You write that symbol down. And then you're going to write the ligands. You're going to put neutral molecules first and then anions. If you have more than one neutral molecule or more than one anion, you're going to put those in alphabetical order based on their chemical symbols, not their names. Okay, so let's do a couple of examples here. Name these compounds. So the complex ion is in brackets to help us see it better. So if we want to name this guy over here, this is in the blue, we name the ligands first. So what's NH3 called? Amine? It is ammonia, but as a ligand it's given the name amine. And CO is carbon monoxide, and that's called carbonyl. So which comes first in the alphabet, A for amine or C for carbonyl? A, thank you. So we've got amine. How many? There's 5. There's 5. So this is penta amine. And how many of these carbonyls? Just 1. So we're not going to use a prefix there. Carbonyl. And then we have our metal. So Mn is manganese. Manganese. And we need a Roman numeral. And then the counter ion is going to be sulfate, right? So we have to do a little figuring to find out the charge on the manganese ion. So sulfate is -2. And so that means this whole thing is +2. All of those ligands were neutral. So the charge on the manganese must. Okay, so now I want you to work on that second one on your own. Okay, did you figure it out? Anybody want to have a go at it?
Sodium chloride planning, but I don't know if it's in. I'm not sure if I put it in order
Okay.
Then what are you talking about?
Yeah. So we name the cation first, which is the sodium. So sodium, so just like ionic compounds, there's two names, a first name and a last name. And so here we've got sodium ions, right? And the complex ion, which in this case has -2 charge. And so then you said tetrachloro, which is correct, 4 chlorides, and chloride is called chloro. And then you were also correct, platinate. Platinum becomes platinate. And then we need a Roman numeral for the metal. So what is it? 2. Roman numeral 2. So here's our sodium. That's the cation. This is the anion. Tetrachloro, there's only the one kind of ligand. Tetrachloro, it's negative, so instead of platinum, it's platinate. And then we figure out the charge. So we had 2 sodium ions, and that balanced this charge, right? So that's how we figured out that this was -2. The 4 chlorides give us -4, and so then the platinum must be -2. I'm sorry, +2. Any questions? It's kind of like a weird puzzle.